Let's try implementing the alternative form of records, the kind with imperative update. So now we're going to do the same thing as JavaScript. When you create a record and it has a field X in it, you can mutate that record, you can imperatively update it so that everyone who's looking at the same record will see the new value for the field. So for this to work, we know that involves state, and we know that state involves allocating memory at some point. So one way we can think about it, the model that we're going to use, is that when you create an object in JavaScript, it's allocating memory for each of the individual fields. And that way, when you update a field, then there's some memory that you can change. You can change the value in that memory. Right? So when we put this in curly syntax, that means we're going to have not set without an exclamation mark, but set bang with an exclamation mark. The bang just reminds the programmer that this is an imperative operation. It's changing something, and that change is globally visible. So I created a record with 2 and 4 as the initial values for A and B, but then I changed A to be 5, so that when I get from that same record R1 the value of the A field, it's going to be a 5. We are going to add begin into our language again, as we do when we have state, so that we can sequence something that changes the state and then something that looks at the state. That's why we get 5 there. As we implement this, what that's going to mean is for each of our fields, we need to allocate memory. And then our set bang can modify the memory, change the value that's of a field at that memory. Now we know in principle how this works from our work implementing boxes in a store passing interpreter. As a first cut, let's just use boxes. Let's assume that we understand how plate boxes work, so let's use plate boxes to implement record boxes. That is, represent the memory for each individual field in a record. So I'm going to change my recv to have a list of symbols still, but instead of a list of values, it's going to be a list of boxes of values. We used to have in our interpreter record E, the interp for that would map interp over the value expressions, and we still need to do that much work, but our recv wants names and a list of boxes of values, not just a list of values. So we need to box each of these individual values, and we can do that by just adding a box around the call to interp. So again, what this is doing is interpreting each field's expression, and then it's allocating some memory in the form of a box to hold that value for each individual field. Our old get used to look like this. We have an expression and a name, and we get a recv, which has a list of names, and it used to have a list of values in it, so that we used this find function that wanted a list of values, and it would return one value. But now we have a list of boxes. What we could do is change find so that it expected a list of box of value, and then it found the right box and pulled the value out. What we're going to do instead, what turns out to be more convenient, is to change find, yes, to take a list of boxes, but return the box. It turns out this doesn't change anything in the implementation of find except its type. It's still looking in 2 parallel lists and finding the right thing in this list to return. And since find now returns a box, and we need to return a value from get, then we put an unbox right there. So writing it this way shows that what get has to do is look in memory somewhere to get the current value for the field after it finds the location or the memory for that field. An advantage of writing it that way is that set can use the same find function. It has the same information, it's got a record, it's got a name, it needs to go find the right box for that name in the field, the field with that name. But since we get a box back now, that means we can change the value in that box. And the value that goes in there is the result of interpreting this v expression. This is almost right. You can see that we're using setbox to implement set, as you would expect. The only detail here is that set has to return a value. And if we make the same choice that we made for boxes before, let's say that the result of an imperative set returns the same value v, or the same value that it gets from interpreting v. So let's let f be the new field value. Let's install that into the box and return the f there. Now, we are cheating in a sense by using plates boxes to implement the interesting part of imperative update. And if you had to, you can go implement records using an explicit store instead of relying on plates boxes. I'll just point out that when you do that, you'll have to rearrange some of the code in bigger ways. For example, in our record E implementation just now, we used map to map box over the interpretation of the v's. But that won't work with a store because each interp needs to return a new store, and we need to allocate a box in that store or allocate some address in that store, and map doesn't communicate the store from one iteration for an element of the list to the next iteration of the element of the list. So you'll have to write your own function or do something else to thread through the store through this sequence of evaluations to make it work for interp with a store.